Okay, here we go. Our second stab at differentiated rate law. So here we are looking at number 1, and it says that this stuff, mercury 2 chloride, reacts with the oxalate ion to produce the chloride ion in solution, carbon dioxide, and something called mercury 2 chloride. We're not really worried about mercury 1 chloride, excuse me. We're not really worried about the products. What we're worried about is the reactants. And it already tells us the order for both of these reactants. Because this one doesn't have an exponent, that's first order. And because this one does, it's a 2, this is second order. So what that means is that whatever we do to the concentration of this stuff, mercury 2 chloride, it's going to have the exact same effect on the rate. If we make any changes to this stuff, it will square that effect on the rate. So here's what this is asking. It says the rate for the reactions was obtained for the first trial and recorded in the table below. Predict the rate of reaction that you would expect to find for the concentrations given in trials 2 and 3. Now, what I'm going to do is I'm going to show you 2 ways of doing this. I'm going to show you the fast way, and then I'm going to show you the long, slow, and complicated way. But the long, slow, and complicated way is going to be instrumental in why we do this. All right? So, make sure you have your calculator ready. I have mine. Here we go. This is trial 1 and 2. Now, we already know the rate for trial 1, and we know that in trial 1 and 2, the concentration of mercury 2 chloride goes from 0.08 to 0.16. It doubles. This doesn't change. So we're doubling mercury 2 chloride. We're not doing anything with this. Because mercury 2 chloride is a first order reactant, whatever changes we make to that concentration is going to have the same effect on the rate. So if we double the concentration of mercury 2 chloride, we will double the rate. All right, that's all you do. Now we're going to do the same thing for the oxalate ion. And remember, this is second order. That means that whatever effect we make on the concentration will square that effect on the rate. If it was a third order reaction, we would cube the effect on the rate. If it was a zero order reaction, nothing would happen. So what we want to do is we want to find a couple of experiments that change the concentration of the oxalate ion, but don't change the concentration of the mercury 2 chloride, and that's experiments 1 and 3. So we're going from, in experiment 1, a concentration of 0.2 molar, to experiment 3, a concentration of 0.4 molar. We have doubled the concentration. Because it's second order, we're going to square that effect on the rate. Well, 2 squared is 4. So now our rate is 4.8 times 10 to the negative 4. That's all that you do. Now, let's take this and do it the long and complicated way and watch what happens. Okay? Let's say that we didn't know any of this stuff, which we do. We'll put that back in there. Let's say that we didn't know any of this stuff. What I'm going to do is I'm going to take an experiment that I already know, and I'm going to find the value and units of the rate constant K. Now watch what happens. So we're going to take experiment 1. I'm not comparing it to anything else. We're going to say experiment 1. What we're trying to find is the value in units of the rate constant K. We know that the order of the first reactant is to the first. We're not even going to write that, and the order of the second reactant is to the second. So we're going to write it like that. What I'm going to do is I'm going to solve for K. So we know that in experiment 1 we have a rate of 1.2 times 10 to the negative 4 moles per liter per second. This is equal to a rate constant K that we don't know. And we know that in experiment 1, the concentration of mercury 2 chloride is 0.08 moles per liter, and the concentration of oxalate is 0.2 moles per liter. We're going to square that. Okay? So let's do that, and we'll solve for K. So now what we have is 1.2 times 10 to the negative 4 moles over liter seconds equals K, which we don't know. This is still 0.08 moles per liter. But we're going to square 0.2, and just to be safe, I'm going to do it on my calculator. We're going to say 0.2 squared is going to be 0.04, but we're just doing this just to be safe, okay? So we have 0.04 moles squared over liters squared. All right? What we're going to do is we're going to take 0.08 and multiply it by 0.04 so we can get this one side. So we're going to take this 0.04, we're going to multiply it by 0.08, and that's going to take care of the value, 0.0032 on this side. We're also going to multiply moles by moles squared and liters by liters squared. So our answer is going to be 0.0032 moles cubed over liters cubed. Okay? So what we're going to do is we're going to solve for K by dividing both sides by 0.0032 moles cubed over liters cubed. And that will give us our numerical value for K. All right? So let's take this. We're going to say 1.2 times 10 to the negative 4, and we're going to divide this by the answer from the previous problem. Stick it right in there, and we get 0.0375. So our answer, our value for K is 0.0375. Look at the units. Look what happens. Moles is going to cancel one of these. It's going to leave that moles squared. Liters is going to cancel one of these. It's going to leave that liters squared. And seconds isn't going anywhere. So we have liters squared in the denominator. The denominator, that puts it up here. And of course, moles squared is still in the denominator. So now what we have is this as our unit. Okay, 0.0375 liters squared over moles squared per second. You're saying, I can hear you saying it. You're saying, Mr. O, why did you waste our time with that? Watch what happens. We already found the answer to experiment 2. We already knew it was 2.4 times 10 to the negative 4. Let's plug these values for concentration into our rate law, whose value for K we now know, and see if we get that answer. So let's go. I'm going to go over here where we have more room. We know that the rate law for this reaction looks like this, where K, the value in units of the rate constant, is 0.0375 liters squared over moles squared seconds. Let's find out what the rate is when we plug these values in for experiment 2. Okay? We already know the answer. We already know it's going to be 2.4 times 10 to the negative 4. We already did that. We did that just by estimating. Now we're going to do it for real. So 0.0375 liters squared over moles squared seconds times the concentration of mercury chloride in experiment 2, 0.16 moles per liter, times the concentration of oxalate in experiment 2, 0.2 moles per liter. And remember that oxalate is second order. So what we're going to do is we're going to crank all this out. Now, before we do anything, let's take care of this guy, which is in parentheses. So we're going to square this. We know it's going to be 0.04. We're going to square the units. We have this now, 0.04 moles squared over liters squared. Okay? Watch what happens, ladies and gentlemen. Now I'm going to take these two values here and multiply them together. So we get 0.16 times 0.04, and this is now 0.0064. More importantly, we're multiplying these units. So we're going to have moles times moles squared is moles cubed, liters times liters squared is liters cubed. The value is 0.0064. So now what we have here is 0.0064 moles cubed over liters cubed. All right? Now, we're going to get the value in a little bit, but look what happens to the units. Liters cubed cancels liters squared and leaves us with 1 liter on the bottom. You follow me? Moles squared cancels moles cubed and leaves 1 mole on the top. Interesting. Moles per liter, and it leaves seconds. So the unit for the rate after we get done with all this is now moles over liters times second. All we have to do is multiply this and this to get the rate. We already know it. It's going to be 2.4 times 10 to the negative 4. Let's verify. So we'll take 0.0064. We're going to multiply that by 0.0375. I'm tired of being so awesome. Boom! 2.4 times 10 to the negative 4. Ladies and gentlemen, that is the purpose of calculating the value in units of the rate constant K. All right? That's all we're doing. Now, if you don't want to do it that way, you could have eyeballed these, which we did the first time. But I guarantee you that now that you know the value in units of the rate constant K, you could plug them into experiment 3. You could plug it into any combination of these reactants, and you would be able to find the rate because you knew the value in units of the rate constant K. All right? I'm going to stop here because I wouldn't have time to do the rest of these, but I'll post that in part 2. Okay, so check this. I hope you listen to this all the way through, because that is a really valuable tool, being able to find this value in units of the rate constant K. All right, see you soon in part 2.